So today's lab is in the dehydration of 2-methylcyclohexanol. And what this lab involves is we're going to take 2-methylcyclohexanol. We're going to add some phosphoric acid to it as a catalyst, apply some heat to the reaction, and we will form two products. And I like this lab a lot because it shows you that when you do a reaction in the real world, you're not just going to have one product that's going to be pure. You're going to have a mixture of products, and you're going to have to go through the process of purifying and identifying them. So for today's experiment, we do this reaction. We do a fractional distillation to remove impurities. We do an extraction to further remove impurities. And then we do a gas chromatography to confirm the identity of our products, and we also do it to find out the composition of the products. So the percentage of one product to the other. So like I said before, to the experiment, we're going to be performing a dehydration reaction. We add phosphoric acid, heat the mixture, and this is going to be done in a round bottom flask, which is attached to a fractional distillation apparatus. And while the reaction is going on, it's a fairly fast reaction, we will be heating it and we will distill it. And we will then collect our distillate. We'll do an extraction. This is mainly to remove any residual acid that might remain, so we don't want that in there. And once we extract it, we pour off our organic layer, and we add some drying agent to it just to take all the water out. And then we decant that into a clean Erlenmeyer flask, and we run a gas chromatography on it to see what we have. Now, this is the general reaction scheme. This reaction is a elimination reaction. Specifically, it goes through an E1 mechanism. So you see in the first step, the hydroxyl group is protonated to form water. The water will then leave and take its electrons and leave behind a carbocation. And depending on which hydrogen is abstracted, we will form either 1-methylcyclohexene or 3-methylcyclohexene. This is the general mechanism, well, not the general mechanism. This is a specific mechanism for each reaction. You can see the first parts are the same. You're going to have the protonation of the hydroxyl group. You're going to have the formation of water, which will leave with its electrons and form a carbocation. The only difference between these two mechanisms is which proton is abstracted on the top mechanism. We see that the proton on carbon 1 is abstracted, forming 1-methylcyclohexene, and on the bottom mechanism, the proton on carbon 3 is abstracted, forming 3-methylcyclohexene. Now, for this lab, you're going to need to calculate the composition of your products for the report. So this is how you do that. I'm going to give you a gas chromatogram. It's going to have peaks on it. We're going to approximate the area under the curve of the peak by thinking about the peak as a triangle. It's a pretty good approximation. So what we're going to do is we're first going to measure the height of the peak. Once we measure the height of the peak, we're going to measure the width of the peak at half the height. And you can see here, that's why the width is called WH divided by 2, because it's the width at half the height. So you see I did that here. And we're just going to calculate the area using the formula for the area of a triangle. And I have that here on the top left. I don't know if you can see my mouse or not, but its area is equal to 1/2 base times height. Under that, I plugged in our values, and I get an area of 20.125 centimeters squared for X, the compound that made this large peak that I labeled X. Now, it's important to note that it doesn't really matter what units you use because they're going to be canceled out anyways. So that's how you calculate the area under your curve, by approximating it as a triangle. Now, to calculate percent composition, I drew in another little peak here. Let's just say the area of peak Y is 9.8 centimeters squared. So all we have to do to calculate the percent composition is we get the area of both peaks and we add them together. So we'll have a total area of 29.925 centimeters squared. And then we just take the area of the individual peak and divide it by the area, the total area of both peaks. So you could see I calculated the percent composition for compound X, and I did this by dividing 20.125, which is the area under the X curve, by the total area, 29.925. Multiply that by 100 and we get 67.25% of the product was compound X. And we can do the same thing for compound Y. Divide 9.8 by the total area, 29.925, multiply by 100, and we find that 32.75% of the product was compound Y. Now, we also need to find the retention times for these peaks. And the way we do this is we draw a line from the top of the peak, the middle of it, all the way down to the x-axis, and the x-axis is going to have units of time. And we just draw a line downwards, and whatever time it lands on, that's your retention time. And you can see here in this example, I landed on a retention time of 3.5 minutes. And that's pretty much it, guys. My references were just the lab manual. If you have any questions, please send me an email.